So let's recall from our video on the printer problem that we had a task to do. This was to say that if the printer has paper and a job in the queue, then the printer should be printing. This is about defining the task of printing. We do not want the printer sitting idle when there is a task it could be completing. Then we asked ourselves, could we break up that problem in a different way, like the one above me? The top line is saying that we have paper and we have jobs to do, we should be printing. Is that the same as saying that if we have paper, then when there is a job to do, we should be printing? It sounds the same, and for simple logic, it is easy sometimes to predict what should happen. But we want to also make sure that anyone who comes along and sees our more complicated logic can see the reasoning that took us from one place to the other. This is what we call in the language proofs. This is a very specific kind of proof. It's one that's so precise that you could follow all the movements of the data, called a syntactic proof. So I want to try to walk us through a proof using just the symbols of the sequent calculus. It's like calculating, like adding and subtracting and multiplying. It's just with new symbols, the symbols that are behind me. They're the ands and implies. You could also add nots and ors, but this one only needs those three, or these two, sorry, so we'll just follow them. All our operations come in two flavors. We have the introduction flavor and we have the elimination flavor. Introduction flavors take the data and produce something with the symbol that we're trying to use. Elimination takes the symbol that we're trying to use and gets rid of it, eliminates it. It's consuming the data that we were using. And keep in mind, this is all about compactifying our arguments. It's not that we can't understand what came before. We're simply using it to package it and to think about it in different orders. So speaking about orders, what orders are behind me? If I look at this, I see that there's a premise, which is a somewhat complicated sentence, and a conclusion, which is also built out of other parts of sequence. So it might help us to separate the two. Think of the premise and the conclusions as two separate data pieces. In fact, we're going to parse this just like we parse any sentence in grammar. So our whole thing is breaking up on one side as the A and B implies C. And on the other side, we have A implies B to C. This is the thing we're trying to do. We're trying to decide if this one entails that one. That's what that symbol means, right? The premise of entailment says whatever came with this premise, you should get to the conclusion. So let's see what's really behind these symbols. We're going to unpack them by unpacking them the way we would unpack a polynomial expression like x squared plus 7 minus 5. We would break that up as a few pieces. What do we break up here? Well, the outermost operation is the implies. That's why we have parentheses here, is to remind us that that's an internal operation. So I'm going to first divide my implication. Now pause for a second and think about which rule what type of rule we're using here. Are we introducing or are we eliminating? We're introducing. We read from the bottom up, and so what we're seeing is that we are going to try to take this data and conclude this implication. And to do that, if we look back at our implication rules here, we see that we only need A to be optional. It doesn't have to be valid to produce the implication. So that means that I'm going to add boxes around here to say, I don't know if A and B is true, but if it were, then I would be able to get the conclusion. All I'm doing, by the way, is just rewriting this premise in a less compact way. I'm finding what it actually meant to have that premise so that I can compare it to the conclusion and see if they're the same. What about this and? How would I create an and? Well, I look back here and I see an and is the conclusion of having an A and a B. So I should backtrack with these arrows. Putting my and symbol in between, I now put the A and then the B on the two sides of my arrow. They're being conjoined into A and B. I'm just following these operations syntactically, but they're already helping me see the key ingredients of this data set. One last piece remains. Since A and B was only an optional observation, we don't know that it's valid, we should pass that along. I don't know that A is valid, and I don't know that B is valid. I'm simply offering that under the conditions that they both were valid, I would get that A and B are both valid, and then I would be able to entail this implication. So that's the structure of the premise. We have an optional A, an optional B, and a guaranteed C under those conditions. So what's on the conclusion side, and would it follow? Let's take this apart by parsing. Once more, I see the outermost thing is an implication, and the parentheses help guide me. The outermost one is that implication. So once more, I have an optional A that I'm taking apart, and it's reaching a B implies C. That data is just looking at my elimination rules, my introduction rule, for implication. Since I want to end with an implication, I must have gotten there from a premise A entailing B, or, if we like, optional A combined with B. That's my picture. What about the rest of this? This seems to be a stopping point, but this can still factor. Over here, I have an optional B, and over here I have a guaranteed C. The implication is again the introduction. We now are done. We've reached the bottom of this side of the tree as well. We have A and B are both optional, and C. Now let me move out of the way. Don't they look the same? That's the key reason we think these are actually entailing one another. We see that on this side, we've simply arranged the ingredients in a different order. We bothered to take the optional A and the optional B and combine them first to then conclude that they would imply C. Whereas on this side, we took the optional B, combined it with C to get the first implication, and then combined it with the optional A to get the second implication. Since these ingredients are available identically to both sides of the premise, they in fact entail them. This side being true would mean that all the ingredients for the left side are true as well. So we can move from that side to the other. In fact, we even see a further property. We could go backwards and have this side has all the same ingredients that that side needs. So we could flip this order and say that in fact, A implies B implies C, furthermore gives us A and B implies C. They're really just packaging the same data in two different ways. Fundamentally, all that's happening here is that we're saying whenever you have A and B entailing C, this side organizes it in one set of languages and this side in another set of operator languages. They're the same content at the bottom. And this is the nature of many programming challenges. What really happens is that to package up a task, we find words in a natural language that help us explain what we expect to have happen. But that can introduce some times elements, some groupings of the information. Where do we put our ands and our conditions? How do we organize our way of explaining to someone else the task we want done? It can package it like the premise. Then when it comes to implementing it, we might have engineering reasons to want to restructure that argument. And so we'll want a different conclusion. In fact, we might even anticipate new needs that somebody else didn't. We might be willing to make a conclusion that's even better than the premise. So we don't have to have that these two are equivalent. Maybe this side is even more powerful than that side. Nevertheless, we can't do less than what was demanded by our management. We need to at least satisfy the premise. So when we make this argument of translating their question into new logic, we should do this kind of a chase to see that they're equivalent. Now, for small arguments, you could just leave this around in your own kind of in natural language. But when it gets really complicated, or you have a bug that you can't chase down, it's enormously powerful to be able to package everything you're saying as a bunch of simple little calculations, little tiny matchings of the patterns with these diagrams. The reason this works is that at the end of the day, you build a tree. Trees have a way to be read identically, one person to the next. Without that, we would struggle to communicate well to other people. The rooted tree is the heart of a proof. A proof is just a tree, gluing together the logical operators that we agree to in context. Keep that context in mind. If you change the background color to yellow, then these facts may no longer be true, and maybe even some of the logical operators might disappear. So always be conscious of the background color of your diagram, and then the rest will be following in a unique, predictable way that could be found thousands of years from now and still be considered true. Until next time. That's how you take care of your chalkboard.